To see the movement of the system, just press on this green button, starting replay. Press on Ctrl G to see the shaded view. Since this FPSO is moving, the attached riser have to move. So we need something flexible here. So as OrcaFlex Beyond, let me talk a bit about flexible pipes. What is a flexible pipe? A flexible pipe is composed of different layers with different materials, and it has a quite desirable bending stiffness. So it is more flexible comparing to steel pipes, and also it has a defined MBR. Why we use flexible pipes? You know, there are a number of reasons that we use flexible pipes. I have listed here a few of them. One of them is flexibility, so they can transport on reel, like the ones that shown in this photo. We can lay them on uneven seabed. Since they are flexible, they can follow the seabed profile. They can stand the dynamics of the hosts used for deep water. For deep water, when we are using dynamic hosts such as FPSO, there are a number of arrangements that I have shown a few of them here, such as this one, we call it lazy wave. If we go for ULS and FLS check, you know, ultimate limited state and fatigue limited state checks, then we will see that motions are beyond the capabilities of the steel pipes. Remember, we did this model. In another session, which I covered the fatigue analysis, I will show you if we put a specification of the steel pipes with the SN curve of them, this configuration and this movement is not standable with the steel pipes. The other benefit of using the flexible pipe is during the installation. Since we mainly use the continuous length of the flexible pipes, we can lay it faster. And even if we do not use the continuous length of flexible pipes, still the subsea connections needed are fewer. The other benefit that I have listed here under modularity, I'm not sure this is a correct word that I am using or not, but the idea is since the flexible pipes are composed of different layers, are similar to composite materials, and we can design them for different situations with different conditions. I may talk a bit about it later. The other benefit that I have listed here and may govern the whole projects is the life cycle cost. So what is the life cycle cost? In any project, in order to prevent any surprises during the life cycle of the project, we should do a cost analysis. I'm not going to provide the detail of the cost analysis, but I should mention that it is composed of two main costs that we know them as CAPEX, the capital expenditure, and OPEX, the operational expenditure. Okay, here I'm going to give you an example of the CAPEX calculations, which is for a small field development in the North Sea. The project consists of 3 production wells and 2 water injection wells. Here you see the 2 cases are considered. As you see, for case A, the FPSO with the flexible risers are used, and for case B, gas lift tieback is used. Okay, more details of the 2 cases are listed here. And if you compare these two numbers, you will see that for case B, the capex value is about 40% higher than case A, which in case A, the flexible risers are used. This is just for capex. You know, as I said, for life cycle cost analysis, we should do the OPEX calculations as well. And at the end, calculate the total cost. Okay, here just I wanted to show you that if we do the life cycle cost analysis, at the end, we may approach for the flexible risers for deep water. Standards and recommended practices are used for flexible pipes. I listed here. The API 17B is the recommended practice for flexible pipes. 17J is a specification for unbonded flexible pipes, and 17K is a specification for bonded flexible pipe. You know, we have two types of flexible pipe that we call them bonded and unbonded. In unbonded flexible pipes, the layers are free to slide on each other. But in bonded flexible pipes, they are not free to move. Let us to open one of these specs, for example, API 17J. Okay, this one is for unbonded flexible pipe. I search for design criteria. There is a table here for flexible pipe layer design criteria, which has different columns. As you see, it has shown different conditions like service condition, normal operation, abnormal operation, installation, factory acceptance test. And in a newer version, there is another column for survival. As you see, for different layers, in different conditions with different load cases, there are different numbers or formulas. For example, for internal carcass, here has given a formula, and for tensile armors, for stress here has given these numbers. And for pressure armors, when we do the stress checking, there are some other numbers. What are these numbers? If you remember the unity check that we mainly use in AST, we mainly calculate a fraction like this one. Sigma is the stress. It depends to the condition that what stress we use. And this sigma y is the yield stress of the material, and N is the utilization factor or permissible utilization factor, which is mentioned in the code. And these are those utilization factors, these numbers. The main codes that we need to use are these three codes that I have listed, but sometimes we may need to have a look to another codes like the ones I have listed here, API 17L1 and 17L2. And sometimes we may need to have a look to other codes such as DMV codes, ASME codes, and the specifications or recommendation provided by the client. Okay, this is a typical cross-section of an unbonded flexible pipe. The layers are shown by some number. As you see, this number 1, 3, 5, and these 5 are from steel. This one is carcass. This one is pressure armor. And these two are the tensile armors. And this one is from polymer, is the fluid barrier. These are tapes, and this one is also from polymer, and we call it outer sheath. Let us have a look at a short video about the layers of an unbounded flexible pipes.
This is the flexible pipe, which consists of an internal barrier. We have a pressure armor layer, tensile armor layer, and then a fluid barrier to protect these layers from corrosion.
Each layer plays a critical role in optimizing the pipeline performance for quality, reliability, and confidence that your operations will run efficiently and consistently. Our hybrid design uses advanced composite materials to replace the metallic pressure armor layer. Customers benefit from less risk by combining new materials within an existing field-proven solution. Our latest integrity management technology, SPIRE, provides continuous monitoring of the outer sheath integrity and detection of a flooded annulus. This data is collected by sensors which are installed with the tensile wires, providing reliable, real-time information, which minimizes downtime and operational intervention.
Okay, let us have a look at a video which shows some aspects of the manufacturing of the flexible pipes. Okay, the code that we use for bonded is API 17K, for unbonded is 17J. The length for bonded is from 12 meter to 100 meter mainly, and for unbonded it could be several kilometers. The content for bonded normally is not for high pressure gas, not for high temperature service, but for unbonded could be for high pressure and high temperature. The maximum inner dia for bonded 24 inch and for unbonded is 19 inch. The bending flexibility for bonded is a bit better than unbonded. The application for bonded is mainly jumper, but for unbonded is for risers, for flow line and jumper. And both of them could be used for production, injection, and export pipelines or risers, but the bonded is not used for gas production. This comparison is typical. For example, this length that I mentioned here for bonded is up to 100 meter. There is a manufacturer I know that can even manufacture for several kilometers. Okay, here you see a typical data sheet of an unbonded flexible pipe which has 9 layers, and you see the description of the materials of each layer and the density and inner dia and thickness and all these data. And we or the manufacturer design the pipes to have a specific design pressure, design temperature, and other requirements. There is a section in API for the failure modes and the potential pipe defects. Since the flexible pipes have different layers, so in different layers, the failure or defects can happen. I have listed the layers here: the carcass, internal pressure sheath, pressure armor layer, backup pressure armor layer, tensile armor layer, anti-wear layer, insulation layer, outer sheath, and this section is included for the end fitting as well. Okay, let's have a look to the API 17B. Search the potential pipe defects. Okay, here has written tables 29 to 31 identify potential defects that apply to the integrity of flexible pipe system. Let's go to table 29. Okay. Table 29, potential pipe defects for static application. This one is for static application. The table 30 is for dynamic applications. For each pipe layer, for example, for carcass, here has given the defects and the consequence, possible cause, and for all this, for all layers has provided. Okay, here I have provided a few photos that show the failure modes. For example, for tensile armor layers, here you can see the lateral buckling. This is for corrosion, and this one is due to the fatigue. And this one is radial buckling that known as bird caging as well. And this one is burst due to the vent blockage at the outer sheet. And these two photos are showing how we can repair them with using ROV. And here, you know, they have installed some kind of repair clamps. And here there was some failures. But this is just for when it is not very severe. Okay, now let me talk about a project that I was involved for ONGC in India. In the RSPBM project, we had 7 flexible pipelines, all water injection with 2 different sizes. The manufacturer was the NKT Flexibles. Now I know they have changed the name. Here you see the flexible pipes are transported on the reel to on board of the vessels that we used for laying. Since the vessel we had was not a flex lay, we designed and manufactured the chute that you see here. The chute is transported on a flat top barge. And in the meantime, the location that we considered for the installation of chute is prepared. We did these cuttings and these welded these stiffeners and prepared it for the installation of chute. And this is a chute that using the crane located at the specified location, I mean here, and it is welded. Then we started the installation. This one that you see is the end fittings, and started from somewhere and continued laying. This is the flexible pipe which has gone through the chute in the water. This is not the end of the story. We installed these 7 pipelines, and an incident happened there, and I want to explain it. Let's first look at the alignment sheet of one of the pipelines. Okay, this is the alignment sheet of one of the pipelines that we're supposed to install. After installation, we did one as-laid survey, and okay, here it looks fine, but as you see here, something is wrong. After investigation, we understood that there was another pipeline job there, and a vessel which used anchors dragged this pipeline. Therefore, we decided to inspect and do the remedial action. After inspecting, we understood that some part of the pipe is damaged, but not severely. We didn't use this kind of clamps that I show here, since the water depth was about 85 meters. So we retrieved the pipeline on board of the vessel and removed the outer sheet of the pipe. This is the removed part. And the technician of the NKT cut some part from this outer sheet, and after placing to this location here, you can see, and repaired it, and we placed pipeline back to its desired location.